On a cold September night in 2024, astronomers detected something that shouldn't exist. A visitor from the depths of interstellar space, traveling faster than anything we've ever tracked before. Not a comet, not an asteroid, something different. For only the third time in human history, an object from beyond our solar system passed through our cosmic neighborhood. And what scientists discovered hiding within this celestial wanderer would challenge everything we thought we knew about the universe beyond our sun. What secrets does it carry from alien star systems? What does its strange composition tell us about worlds we've never seen? And could this cosmic messenger hold clues about the very building blocks of life itself? Our story begins not with a telescope pointed at the stars, but with a warning system designed to protect Earth from cosmic threats. The Atlas Survey, the Asteroid Terrestrial Impact Last Alert System, operates like a sentinel, constantly scanning the heavens for objects that might pose a danger to our planet. It's a network of robotic telescopes spread across the globe, tirelessly watching, waiting, cataloguing everything that moves against the backdrop of stars. On September 13th, 2024, Atlas detected something unusual. At first glance, it appeared to be just another comet, a fuzzy point of light drifting through space. But as astronomers around the world turned their instruments toward this mysterious object, they realized something extraordinary. It was moving wrong. The trajectory was all wrong for something born in our solar system. The mathematics were unmistakable. This object wasn't orbiting our sun, it was passing through like a traveler on a cosmic highway that stretched between the stars. They designated it C2024S1 Atlas, but as the observations mounted, that classification would change. This wasn't just another comet with a catalogue number, this was 3I, the third confirmed interstellar object ever detected by humanity. Think about that for a moment. In all of human history, across all our telescopes and all our observations spanning centuries, we've only confirmed 3 visitors from beyond our solar system. The first was ʻOumuamua in 2017, that strange, elongated object that tumbled through space like nothing we'd ever seen. The second was 2I Borisov in 2019, a comet that looked reassuringly familiar, proving that at least some things out there resemble what we know. And now, 3I Atlas, the newest member of this exclusive club. But what made it special wasn't just where it came from, it was what it was made of. As observatories across the planet tracked 3I Atlas through the autumn skies of 2024, spectroscopic analysis began to reveal its secrets. And those secrets were puzzling. When sunlight hits a comet, it excites the molecules on its surface and in its atmosphere, what astronomers call the coma. These excited molecules emit light at specific wavelengths, creating a spectral signature as unique as a fingerprint. By analysing this light, scientists can determine exactly what a comet is made of, down to the individual chemical compounds. What they found in 3I Atlas was unexpected. The spectral data showed strong signatures of carbon monoxide, far more than typically seen in comets from our own solar system. But it wasn't just the abundance that was strange. The ratios were off. The relationship between carbon monoxide and other volatiles like water ice and carbon dioxide didn't match the patterns we see in comets born around our sun. Dr. Michelle Bannister from the University of Canterbury, who led one of the observational teams, described it as finding a recipe written in a familiar language but with proportions that make no sense. You recognise the ingredients, but the dish is something you've never tasted before. This compositional oddity tells us something profound about where 3I Atlas came from. You see, comets are time capsules. They're frozen relics from the birth of planetary systems, preserving the chemical conditions of the protoplanetary disk from which they formed. The fact that 3I Atlas has a different chemical makeup than our local comets means it formed under different conditions around a different star in a different nebula, perhaps billions of years ago. But the carbon monoxide story gets even more interesting. The abundance of CO suggests that 3I Atlas might have formed in an exceptionally cold environment, colder than the outer reaches of our own solar system. This points to origins in the outer edges of another star system, perhaps in the equivalent of our Oort cloud, that distant shell of icy bodies surrounding our Sun at the very frontier of its gravitational influence. As weeks passed and 3R4 drew closer to the Sun, astronomers noticed something else unusual. It was behaving erratically. Comets are predictable creatures, generally speaking. As they approach the Sun, solar heating causes ices to sublimate, to transform directly from solid to gas, creating the characteristic tail and coma that make comets so spectacular. This outgassing also acts like tiny rocket engines, slightly altering the comet's trajectory in ways that can be calculated and predicted. But 3I Atlas wasn't following the script. The object was exhibiting non-gravitational accelerations that didn't match models. It was speeding up and slowing down in ways that suggested either an unusual structure or an unusual composition, or both. Some researchers proposed that the comet might have an extremely porous structure, more like a loosely packed snowball than a solid chunk of ice and rock. This would explain why outgassing was occurring in unexpected patterns. High-resolution imaging from the Hubble Space Telescope and ground-based adaptive optics systems revealed that 3I Atlas possessed an asymmetric coma. The cloud of gas and dust surrounding its nucleus wasn't uniform. Jets of material were erupting from specific locations on the surface, creating a lopsided appearance that suggested the nucleus itself was irregularly shaped or had regions of different composition. Then came the fragmentation. In late October 2024, observers noticed that 3I Atlas was beginning to break apart. Small fragments were splitting off from the main nucleus, each following slightly different trajectories. This wasn't entirely surprising. Comets are fragile objects, and the stress of passing close to the Sun can tear them apart. But for 3I Atlas, this fragmentation provided a unique opportunity. When a comet breaks apart, it exposes pristine material from its interior, material that has been protected from space weathering and solar radiation for billions of years. It's like cutting open a geode. The inside reveals truths that the weathered exterior conceals. Spectroscopic analysis of the fragments showed subtle variations in composition, suggesting that 3I Atlas wasn't a uniform object, but had layers or regions of different material. This layered structure supports the theory that 3I Atlas might have formed through the gentle collision and merger of smaller objects in its birth system, a process called hierarchical accretion. Each layer might represent a different formation event, a different moment in the early history of that distant planetary system. Where did 3I Atlas come from? This is perhaps the most tantalizing question, and one that astronomers race to answer. By carefully tracking its trajectory and running the calculations backward, researchers could trace 3I Atlas's path through the galaxy. The orbital mechanics are complex, involving not just the gravitational influence of our Sun, but also the gravity of every planet it passed near, the pressure of solar radiation, and even the cumulative effects of outgassing. The backward integration tracing its path into the past revealed that 3I Atlas approached our solar system from the direction of the constellation Cassiopeia, but pinpointing its exact stellar origin is far more challenging. You see, stars move. Over the millions of years it might have taken 3I Atlas to travel through interstellar space. Both it and its parent star have moved significantly. Several candidate parent stars have been proposed. Advanced computational models have identified a handful of stars in that region of the galaxy that could potentially be the home system of 3I Atlas. These stars show similar chemical signatures, specifically enrichment in carbon that would be consistent with producing comets like 3I Atlas. One particularly interesting candidate is a young star system located approximately 450 light-years away. This system, designated HD 26965, has been observed to possess a debris disk, a ring of dust and rocky material similar to our own Kuiper belt. Could 3I Atlas have been ejected from this system during a close encounter with a massive planet, or during a stellar flyby with another star? It's possible, though we may never know for certain. What we do know is that 3I Atlas has been wandering the galaxy for a very long time. Estimates suggest it could have been travelling through interstellar space for anywhere from 1 to 10 million years. During that time, it would have been exposed to cosmic rays, interstellar dust, and the harsh radiation of space. Yet despite this long journey, it retained enough volatile material, those light, easily evaporated compounds like carbon monoxide, to create a coma when it finally encountered the warmth of our Sun. This resilience tells us something important about the nature of interstellar objects. They're tougher than we might expect. The galaxy isn't empty. Even the vast spaces between stars contain trace amounts of gas and dust. Objects traveling through this medium would experience erosion over time, like a spacecraft experiencing drag. The fact that 3I Atlas still possessed a substantial volatile inventory suggests either that it had a protective crust that insulated its interior, or that the interstellar medium is less erosive than some models predict. Now here's where things get really interesting. The discovery and analysis of 3I Atlas has profound implications for one of the most exciting questions in science. How common are the building blocks of life in the universe? Comets like 3I Atlas are essentially delivery vehicles for organic chemistry. They contain not just simple molecules like water and carbon monoxide, but complex organic compounds, carbon-based molecules, that are the precursors to the chemistry of life. Previous studies of comets in our own solar system have found amino acids, sugars, and other prebiotic molecules. If comets from other star systems carry similar inventories, it suggests that the chemical foundation for life might be widespread across the galaxy. But 3I Atlas adds an additional layer to this story. It's not just that organic molecules exist in other star systems, we already suspected that. It's that these molecules can travel between star systems. Think about the implications. If objects like 3I Atlas regularly traverse the galaxy, and if they carry organic compounds with them, then the galaxy might be engaged in a form of chemical exchange. The building blocks of life in one star system could in principle be transported to another. This process, called panspermia, has been speculated about for decades, but interstellar visitors like 3I Atlas make it seem not just possible but likely. Research teams are now analysing the spectra of 3I Atlas, specifically looking for biosignatures, signs of organic complexity that might hint at prebiotic chemistry. Preliminary results suggest the presence of complex carbon chains, though confirming specific molecules from such distant observations is challenging. The fragmentation of 3I Atlas has actually helped here, as the exposed interior material shows stronger organic signatures than the weathered surface. Dr. Karen Meach from the University of Hawaii, a veteran of interstellar object research, suggests that we should think of objects like 3I Atlas as seeds drifting through the galaxy. Just as dandelion seeds scatter in the wind, these cosmic seeds carry the chemical information necessary for life to emerge. And just as some seeds will land in fertile ground while others will not, some interstellar objects will be captured by star systems while others will continue their journey through the void. 3I Atlas is teaching us that interstellar visitors are more common than we once thought. Before ʻOumuamua's discovery in 2017, we had theories about how many interstellar objects might pass through our solar system, but no confirmed detections. Now, with 3 confirmed visitors in just 7 years, we're beginning to revise our estimates upward. Current models suggest that at any given moment there might be several interstellar objects within the orbit of Neptune. We just haven't seen them yet because they're small, dark, and moving quickly. As our survey capabilities improve with next-generation telescopes like the Vera C. Rubin Observatory coming online, we expect to detect many more. This has exciting implications for future space missions. There's serious discussion in the planetary science community about designing a mission that could rendezvous with an interstellar object. Imagine actually landing on a visitor from another star system, drilling into its surface, analysing its composition in detail. The technological challenges are immense. Interstellar objects move fast, and launching a spacecraft to intercept one would require catching them early and having a rocket ready to go at short notice. But it's not impossible. NASA and ESA have both commissioned feasibility studies for interstellar object intercept missions. The key is detection lead time. If we can spot an incoming object years before it reaches the inner solar system, we might have enough time to design, build, and launch an intercept mission. 3I Atlas, unfortunately, was detected too late for such a mission, but future discoveries might offer better opportunities. As of early 2025, 3i Atlas has fragmented into dozens of smaller pieces, each following its own trajectory out of the solar system. These fragments are being tracked as they recede, growing fainter with each passing week. Soon they'll be too faint even for our most powerful telescopes, and 3i Atlas will return to the darkness between the stars from which it came. But the data remains. Thousands of spectra, millions of positional measurements, countless images, all catalogued, all waiting to reveal their secrets. As our analytical techniques improve and our models become more sophisticated, we'll continue to extract new insights from this brief cosmic encounter. What's particularly exciting is that 3i Atlas won't be the last. The Vera C. Rubin Observatory, currently in final commissioning in Chile, will begin operations later this year. This revolutionary telescope will scan the entire visible sky every few nights, detecting objects far fainter than current surveys can see. Estimates suggest it might detect one interstellar object per month, possibly more. We're entering a new era of astronomy, one where interstellar visitors are not rare curiosities but regular occurrences. Each one will be a messenger from distant shores, carrying information about star systems we'll never visit in person. Each one will tell us something new about how planetary systems form, how common our own solar system's chemistry might be, and what variety of cosmic environments exist across the galaxy. 3i Atlas has shown us that the universe beyond our solar system is not as distant as it seems. These visitors remind us that we're not isolated, we're part of a dynamic galactic ecosystem where matter, and perhaps even life's building blocks, flow between star systems like ocean currents, carry nutrients between distant shores. The story of 3i Atlas is, in many ways, just beginning. Though the object itself has passed beyond our ability to observe it, the questions it has raised will fuel research for years to come. What it found in 3i Atlas was a cosmic Rosetta Stone, a key to understanding the chemistry of distant star systems, a glimpse into planetary formation under alien suns, and perhaps even a clue about how common the ingredients for life might be throughout the galaxy. As we look to the future, to the coming wave of interstellar detections, we're reminded of something profound. We are not separate from the rest of the galaxy. We are connected to it through these cosmic travelers, these wandering messengers that bridge the impossible distances between stars. The universe, it turns out, is not as lonely as we thought. And every time an object like 3i Atlas passes through, we learn that the cosmos is far more connected, far more dynamic, and far stranger than we ever imagined. Thank you for watching. If you enjoyed this deep dive into one of astronomy's most exciting recent discoveries, please like and subscribe. And let me know in the comments, what do you think we'll discover when we finally intercept an interstellar visitor up close? Until next time, keep looking up.